So we'll talk today about the this year's update of the James Webb Space Telescope hardware and science, the faint object time domain and POP3 Caustic transits. There's a large team there of folks involved. I'll have a few more slides on this during the Bacall lunch talk on a different topic of reionization. But here it will suffice to say that today the JWST science remains as compelling as it was 20 years ago, or even longer than that when the concept first started, even before JWST's launch. In fact, I would say the science today is far more exciting than we could have imagined for 2 decades ago. So there's a link there to the talk, and Roman has it. He can email it around. Let's see. I need to make sure that going to the next page works. There we go. So this is the outline for the talk. Hardware, number one. Then the time domain science. Apology for my dog in the background. There's folks walking on the street here. In particular, the North Ecliptic Pole continuous viewing zone, a field that nobody's ever looked at until a few years ago. Turns out to be the best field to observe at JWST. You can observe it around the clock. So that's for variability of faint objects like AGN, brown dwarfs, other things. Very high redshift supernovae, including pair instability supernovae. There's already teams writing sequel proposals for this. They're due in a few weeks, as you know. And then not to forget one of the darkest skies that JWST can see if all goes well with the deployment. And that could be very useful for CIB fluctuations and to constrain the first light sources. Talk about that a little bit too. So this will be a community field for time domain science over the minimum lifetime of JW 5 years, the maximum propellant lifetime of 14 years, and the first epoch public right away so that the community can jump on it, and the other epochs to follow very soon. Then we will monitor the best lensing clusters for possible caustic transits of individual POP3 stars, so not star clusters or galaxies. There will be that too, but individual stars and the stellar mass black hole accretion disks at redshift bigger than 7. And we believe this is possible. We have seen some of that at lower redshift with HST. So we'll use the limits to the sky brightness from the first stars and the stellar mass black holes to see how many of such POP3 star caustic transits we might see. And it turns out if you observe a couple of clusters a few times a year, you might get lucky. I'd like to dedicate this talk to the memory of John Bacall and Lyman Spitzer, who taught us to fight for missions we believe in. On that topic, both Hubble and James Webb are 30 to 40 year projects. In fact, Hubble a lot longer than that. It started in the 1960s. To be fair, Lyman Spitzer already thought about Hubble shortly after World War II. And Hubble, after being launched in 1990, is still going on today. James Webb, of course, started longer than 20 years ago. And by the time it's all said and done, it will be well over 30 years. So you will feel wrinkled before you know it. Jim Gunn, I got this chart from Jim Westphal's office, and he obviously wrote it for HST. You might recognize the chart. So I rewrote it for JWST, but it's still true today. So these are missions that last a good fraction of human lifetime. Hubble, of course, is a 2.4 meter mirror, JWST 6.5 meter edge to edge, and therefore, at 2.5 times larger wavelengths than Hubble, it will have the same resolution in the near infrared as Hubble has in the optical. And at the same wavelength, there's a small range of overlap. It will have 2.5 times better resolution. And of course, much better collecting area, and also a much darker sky in the infrared than Hubble has in L2. It will go up on an Ariane 5. The launch vehicle is already being built. It takes less than a year to build these, and they will be ready for us next summer. And we will be 6,200 kilograms, a few hundred under limit, and launched from French Guiana, from Kourou, and the sitting in the upper stage here, of course, of the Ariane 5 launch vehicle. So when we leave the Earth here in the center of the spider web, go past the orbit of the moon, this white circle, we get to L2 about 5 times further away. It's not a single point. It's not a stable Lagrange point. It's actually quite large, of the order of 10 to the 18 cubic kilometers. So over here, we will describe a Lissajous figure vertically and horizontally about 1 million kilometers in diameter. So we will not run into any space debris like artificial satellites like Herschel, WMAP, and Planck. They just drift out if they don't get properly course corrected to stay in L2. In L2, of course, we go with the Earth around the Sun every 365 days. And if my cell phone, I hope you can see all this, is the Sunshield, the whole idea is that the telescope, and if I'm the Sun, and its instruments are well behind the Sunshield at all times. From this vantage point, you can observe the sky for about 70% of the time, as opposed to low Earth orbit, where it's 50% of the time, slightly more because the Earth is curved for Hubble. Hubble has had more than 200,000 sunrises and sunsets since it was launched, every 96 minutes. But James Webb will have one sunrise when the launch fairing opens and one sunset when the Sunshield deploys, if all goes well. And so it's a much more stable thermal platform than Hubble is. Feel free to ask questions during. I will have a natural break in the middle when we stop talking about the hardware and go talk about the science. This is the family portrait. 100% is now built. More than 99% weight. They reserve the right to put some counterweights in. The center of gravity is in the right place, so that's probably not needed. Primary mirrors over here, upper left. Secondary mirror before it was gold coated, lower left. Tertiary mirror and fine steering mirrors in the upper right. And then all the spacecraft structure, support structure, everything else, Sunshield, electronics, spacecraft bus, made in the last couple of years and assembled since the early 2010s. So it's all there. This was the assembly package in schematic form. The instrument package, of course, is here in this housing. This telescope support structure, the 18 beryllium mirrors, and the secondary support structure, all put together in the last 5 years and in the last 2 years, 3 years being tested. This is the telescope after it was put together with the dust covers on. NASA was initially not inclined to put dust covers on. I prodded hard to make sure that they were put on, and we had the hunch that it might be staring at the ceiling for a few years before it would be launched. So we have dust covers, and how do we put them on? Well, very carefully with 2 NASA employees on Olympic diving boards. Don't drop the dust cover. This little doghouse in the center is the baffle through which the light comes from the secondary. There's a cover plate here to protect it from dust. Obviously, we want to be very cautious about dust and deposits on the mirror. After all, this telescope is designed to find water in the atmospheres of Earth-like exoplanets, so you don't want any ice crystals or dust particles left on it. I should say, for the sake of completeness, that twice it was exposed to proximity of a large amount of water here in building 29 in Goddard, where Hubble once was in the winter of 2016. There was about 2 Olympic swimming pools worth of snow on the roof during the snowstorm of January. And when it was tested in Houston in 2017 in the last thermal vacuum chamber test, there was about a cubic kilometer of water that came by during Hurricane Katrina. Of course, the telescope is being well protected, and even today it is being carefully inspected for dust particles and so on. You've seen this room before, probably. Notice the NASA logo here on the wall, and the technicians on the floor. There's this big merry-go-round on the floor that allows you to move the telescope every which way. This was in 2017, I think, when it was fully constructed. Here is the team in the foreground with John Madder, the project scientist who cracks the whip. You can see that the NASA logo, which is now behind us on the wall, is actually shown in the mirror, and it's enlarged. So the mirror works, it's doing its job. We haven't tested it to the required level, of course, but at least it's doing what it's supposed to do. And it's big. So there it is once more before it goes into a chamber to be tested in full. And that's, of course, no small business to get that right. Here's the 4 instruments. I'll spare you all the details, but there is the Canadian fine guiding sensors with the 2 guide probes that hold the telescope still while it's taking long exposures for imaging or spectroscopy, the U of A near-infrared camera that works between 0.7 and 5 microns. The near-infrared spectrograph, same thing, except it can take spectra of hundreds of objects at the same time through various modes. We'll talk about that a little bit more. And then, of course, the European also mid-infrared instrument made by ESA and significant JPL and U of A involvement that will work between 5 and 29 microns, both for imaging and spectroscopy. All very popular instruments, it turns out. A lot of proposals already being submitted with exposure time simulator calculations being requested for all of them. So just for the record, 27 US states and Canada, of course, involved, actually more than 27 states today. That was politically critical to survive the various budget overruns we unfortunately had. And 16 European countries and Canada, as I said, all critical in making this hardware as well as the launch vehicle. Without the international support and presence, we could not have survived, and we would not have survived. You're probably all familiar with this, the micro shutter arrays for the near-infrared spectrograph. If you have a deep field like a star cluster or a galaxy cluster or an ordinary deep field, you will know in advance where your objects are. You can open up these little louvers. They're 0.2 by 0.4 millimeters. They opened up magnetically. And they can be closed magnetically as well, more or less at will. And so you can open them up where you expect the galaxies or the stars to fall, and you can take many dozens up to 100 or more spectra at the same time, even this spectra in the same row, because the spectra are not quite the size of the whole array. You can make any pattern here, including the JWST logo, which is not very useful for astronomical purposes, but you can. You can see that this logo shows some shutters that are failed closed, which is a better thing than failed open. There's a couple of them that are failed open and they have been epoxied over. That's one of those things you have to do. This is probably the most fragile part of the entire telescope, and we have lost some shutters during the various shaking and so on that was expected. So the system isn't perfect. If you're interested in this galaxy and the shutter there is failed, then you need to take a next exposure where you move the telescope. That's spectroscopically, as you all know, the correct thing to do anyway. You want to subtract the sky, even though it's very dark, as accurately as you can. So this was in 2019, more than a year ago, checking the secondary. I have movies of this. I rather not show them because they take forever and they don't always work. But this will work as well. With the merry-go-round, it's now in the horizontal position, if you wish, and you can see technicians running around to make sure that the secondary mirror, which comes with redundant mechanisms, there's a mechanism here and a mechanism there, to make sure it gets put into place, like this, excuse me, going the wrong way. While you see these folks do that, you see actually cables from the ceiling. That is not to help the mechanism, but it's to offload the gravity. You would destroy the mechanism if you let it do the full force thing in one gravity, even if you hold the telescope horizontal. So that's how you have to test. That is true for many things. You want to make sure that the weak motors, which can't produce more than such and so force in zero gravity when they do the actual deployment, don't do any damage on Earth when you test it. And that's part of the tricky business that we had to go through. So then a few years ago, during Hurricane Katrina, we took the telescope to the main chamber in Houston. It doesn't quite fit in the overhead compartment. This is the NRO enclosure that takes a 36-wheeler, 2 freeway lanes. The whole thing fits in a C5, just barely. And that big door in the background is the same vacuum chamber where the Apollo capsules were tested in the 1960s for the moon landing. So the moon lander and the capsule, not the entire Saturn V, of course, but it is the largest thermal vacuum chamber in the world. So the entire telescope gets rolled in, deployed, and then stare at the ceiling where there's a set of complicated wavefront sensing apparatus that produces the correct beam to be tested and make sure that we can focus and get all the mirrors aligned. This 14 mirror door then closes. You remove everything you don't want in there, you pump it vacuum, you bring it down with a helium shroud to 45 kelvins, which is what the Sunshield will hopefully also produce when we get to L2, and you test the thing. The hardest part was probably the Sunshield itself. It's tennis court size. It's these 5 layers of Kapton that come up vertically along mechanical arms, and they're mounted on these 2 big pallets. We call them garage doors or UPSs, unified pallet structures that hold the Sunshield down during launch with various mechanisms that need to be doubly redundant, retract when the deployment happens. Here you can see this happening in the last year and a half at Northrop Grumman, where the Sunshield was put together for final assembly and testing. There it is vertically before the telescope gets inserted. This is just a dummy structure in the middle, of course, but the entire flight Sunshield is on these 2 vertical pallets here, which sits like the the wings of a bat besides the telescope during launch inside the launch fairing. Here's the telescope before it gets mounted with the 2 3 mirror side panels folded backwards still, of course, and that also gets deployed and lowered from the ceiling here onto the Sunshield. That happened over a year ago. And this was then the first time we had a observatory, not working yet, of course, but where all the pieces were put together with the telescope on top of the Sunshield, and of course the secondary mirror hanging towards the back. Picture from the other side. And at this stage, in the last year and the coming half year, it is a matter of testing it all, in particular testing whether the Sunshield itself deploys along these vertical arms with mechanical pulleys, and that had to be tested several times. You can't test it too often. Test it more than 10 times, there will be an undue number of tears in the Sunshield. There's already a couple of small tears, you know, millimeter size in there that they glue over, but they also had to make sure that nothing gets stuck during this deployment. So they have done the deployment now 4 times, I think, and they're going to do it once more in the current half year. It takes several months, especially the folding up. The deployment itself doesn't take that long. Of course, in orbit, it will only take a few days. But folding it all back up to make sure it deploys again is a lot of work. So this is probably the single biggest cliffhanger that we need to deal with in orbit. So
Roger,
here is, go ahead.
From Michael Strauss.
Yeah, go ahead, please.
Yeah, so I'm seeing all these beautiful pictures with the mirrors exposed. You say, of course, that dust is a bad thing, but how sensitive are you to dust? I mean, how clean do the mirrors have to be? How do you make sure that they remain clean? As you said, they have to be sitting there for years staring at the ceiling. Well, how sensitive are we to the dust?
We will have between 0.5% and 1% coverage, we think. But there is another round of cleaning before we launch. I was told 20 years ago I could never use 2 words. The word parallel for parallel observations and the C word for cleaning. They have changed their mind on both topics, fortunately. We will now have science parallels and we will have cleaning. They do it very carefully with brushes and suction devices. And these folks you saw on, Michael, on the Olympic diving boards will also hover over and do more cleaning, probably in the vertical position. So there will be another round of that before launch. It is harder now. The telescope is for good mounted on top of the Sunshield, so it is more risky to hover over the Sunshield. When it was not sitting on top of that, it was easier to clean, but there will be one more round. The expectation is that, of course, there's lifetime accumulation in L2 as well, macrometeorite damage, other things that may freeze onto the mirror. That we will have less than 1% coverage, but there will be some of that, and it will take some of the mirror transparency away, and probably will create some spectral features in what you're trying to observe. I hope
Thank
that's an answer to your
Yes,
question.
thank you.
Yeah.
Thanks very much.
Yeah, but yes, we held their feet to the fire on this one, and I'm very glad we did, because we would launch with as clean a mirror as possible without wreaking other damage or havoc. So here is the solar panels. There's 5 solar panels hanging from the ceiling, of course, with a motor that deploys them like this. And that, of course, has to be tested vertically in 0 gravity or 1 gravity vertically, almost 0 gravity, just to make sure the motor does its thing, unfolding that those 5 leaves. And that has been tested and is being one of the last things actually being installed this next month. Actually, it's already there, but they needed to take it off once more to get to something behind it. But it will sit right there at the bottom of the spacecraft and, of course, fold open a few hours after launch. We have battery power. In fact, the thing that's being done this month is put a new battery in, also somewhat of a concern. The old battery been around for 10 years, so there was a new technology with longer longevity and more charges. So we have a new battery now this month that will allow us to survive for 7 hours in orbit without the solar panels being out yet. So yes, they have to come out soon after launch. Here's what you can see is the upward deployment also against gravity with that yellow crane at the top here of the deployable tower. The telescope has to move up, by about 1 meter, as you can see here, to be above the sunshield, so that then the sunshield can deploy horizontally. So that's one of the first steps that happens in orbit after the sunshield or the solar array deploys. Then the 2 side panels with the sunshields, move up for launch and move down for testing. You can see that's being done here. Again, the trickiest part is to test all of this in 1 gravity and make sure the motors work but don't get overloaded. So you can see that here. And this happens in the last month or 2. The very last thing we did in August is move the whole thing. One of the more riskiest part of other than the launch and the deployment itself, of course, across the parking lot from building A to building B at Northrop to do the last vibration tests. And the concern here was what happens if you have a major earthquake during the move. Well, there was an earthquake, but not during the move. It happened when the telescope was in the chamber, all wired up for the acoustic and vibration testing. And yes, they could measure the earthquake. And no, it didn't do any damage because it was only a Richter 4. But yes, it can happen. You want you want to get this thing out of California. So, but anyway, it did on October 5, so a month ago, pass its last acoustic test without further hiccups. As you may know, 2 years ago, they dropped some nuts and bolts on the floor during the test. Not a very pretty thing. Out of 3,200 nuts and bolts that hold the sunshield cover down, about 17 came loose during the vibration test in 2017. So obviously that was a user error. They didn't put epoxy on top of some of these, and they now have. So this won't happen again, and it hasn't happened again. So we're ready for the science part now. I don't mean to race through this. So we have some time for more hardware questions before I get to the science. And
I think we have some. Ed Jenkins had a question.
Yes, please, Ed.
Yeah, I have a question about what I heard some time ago, that the bolts that release the hardware, there's something like of order of 100 single point failure possibilities. How concerned are you about that?
Well, initially very concerned. 15 years ago or so, when the sunshield was first studied in detail, I think going back to 2005 now, the answer from Northrop and Nexolve, who makes the sunshield, was trust us, we know what we're doing. And my response to that was, yeah, like Ronald Reagan said, trust but verify. So it's a ballpoint type device. There's 103 of them that needs to come down. It's a mechanical retraction by, I think, about 2 or 3 inches. And there is 2 mechanisms to do it: a backup and a primary mechanism. And they both get fired. And when they test every one of these 26,000 times, and if it doesn't work, they throw it out. And so the 103 they had mounted this last year One of them, the backup retraction failed, but the primary succeeded. And so it is a concern, but this is why you have a backup and a main retraction mechanism. It did succeed, and they're going to do that once more.
Now, if one of them fails, is the whole mission doomed, or is it just that it would operate at reduced capability?
It depends where. If it's in the middle, then you can't deploy the Sunshield. If it's at the edge, you might deploy it partially, which is also not good. You don't want to expose the mirror or the instruments to the sun. But yeah, they all 103 of them have to retract. It is not something I would have designed this way, but keep hearing from the industry, we know what we're doing. We've built these kinds of things. And yeah, to put it differently, Ed, you and I looked at Hubble a long time ago, its budget and its planning. So what I keep hearing from the, not the main contractor, but Ball Aerospace, is that this is the smallest one they ever built. They've built larger ones of this kind at much lower surface accuracy. So it's not the size that scares them, it's the surface accuracy that's needed for K-band diffraction limit. And we have that, but that was the hardest part and also the part that drove the budget the most.
Do we know how many have failed in orbit that they haven't reported?
They won't tell you about the Sunshield and the deployables. I have a chart saying that, well, the chart is now 10 years old, but back then Northrop had 4,500 actuated faults in space and never had a mission critical failure. If that's a number to go by, it's probably double that by now. I haven't heard of any big missions that they lost. I mean, they've done many things that we know about, such as Chandra and down-looking, Earth observing things such as Aqua and Aura, all public missions, and they've done other things that they can't talk about. But they got a pretty good track record in making things work in orbit. Having said all that, this is, not without risk. Good question, Ed. I hope I gave a good answer. Any other questions?
I think we don't have any more.
Yeah, I saw the question in this chat here on my other computer. So this is why you test many times. You don't want to over-test, but you certainly don't want to under-test. All right, so then we go to the science, the North Ecliptic, South Ecliptic poles. So unlike Hubble, where you go around the Earth every 96 minutes and you can observe slightly more than 50% of the sky at any given time, of course, depending on where you are around the sun. With James Webb, it's this green band around the sky vertically that goes 45 degrees down from the North and South Ecliptic pole, which are the vertical line here, and it goes about 5 degrees back. The Sunshield is made such that it's this 45-degree angle of objects in the sky all around the anti-sun direction that we can observe at any given time. And this green band, of course, goes around the sun with the Earth every year. And that's why every 2 months you can observe any object you like within a 2-month window, and then you have to wait 6 months for it to come back at the other side, which is pretty much like Spitzer operated, except Spitzer was further away from the Earth. The CVZ, the continuous viewing zone, which happens to be partially also in the Hubble CVZ, and that's why it's of such great logistical interest. You can observe it all the time from both telescopes. Hubble not quite all the time, but more often than not. And with James Webb, there's no limit to observing here and down there within a radius of 5 degrees, except that if you stare too long, you will start using propellant, because you have to use propellant to dump the excess angular momentum out of your reaction wheels, right? With Hubble, you have magnetometers in the Earth's magnetic field, in the Van Allen belts, that help you dump the angular momentum. Here in L2, you can't do that. You're outside the Van Allen belt. So if you stare at one spot too long, you have to use propellant. So
how long is too long?
Well, if you got 200 hours to do an ultra deep field, if I were the Space Telescope director, said, I'm not sure I want to observe that all at once, except if you also observe, after 200 hours in the north, go 200 hours in the south, that would be okay. Then you can spin the wheels to do that. But then you have to go back and forth a number of times. And slewing, of course, it takes more than half an hour to slew across half the sky. So almost an hour to slew across the sky. It's not fast. These reaction wheels are only 20 kilograms. You need to steer 6,300 kilograms. So, but yeah, a couple of hundred hours at the same spot, you need to worry about stopping and going somewhere else to unspin the reaction wheels.
Roger, we have a question.
Yeah, please.
Jeremy.
Yes, Jeremy.
It's probably a silly question. I haven't tried to do the arithmetic, but can you get rid of any angular momentum with radiation pressure? Or if you had a reflective panel that you were willing to expand to get a larger lever on?
There is not a lot of that. I think the Poynting Robertson drag on the Sunshield is not insignificant. We have it's a flap at the end of the Sunshield that helps balance that. But we're always pointing away from the sun, sort of symmetrically. If my face is the Sunshield is like this, the telescope is over here. And so the Poynting Robertson drag on both sides of the Sunshield, I don't think will create great asymmetry. It's not something we're counting on. Does that answer your question? Good question. Yeah. So it's primarily pointing too long in the same direction that makes the reaction wheel spin up. And then after a while, you just have to go somewhere else. But, there is several thousand observers that want to use this telescope, so there should be no lack of targets. So the North Ecliptic pole is not at very high galactic latitude, about 33 degrees, and it has some cirrus. So if you want to pick a perfect spot there, you need to get creative. To the left is a WISE map of 4-micron stars, where red is bad and blue is good. And we found a spot here. It's over here somewhere where my cursor is, over here in the Schlegel et al. EB-V map. It's relatively clean. The EB-V is less than 0.03. It's not perfect in terms of a high latitude region, but it's relatively clean. And it has no bright stars. Anything brighter than 16th magnitude in K-band would create persistence and not allow you to do very long integrations without creating other havoc. So we're going to that spot. We call it the North Ecliptic pole time domain field. And for the record, the one in the south isn't so good because there is a galaxy there called the Large Magellanic Cloud, which pretty much clobbers that up. Now, that's a target, of course, of great interest to many other people. So I don't want to minimize it. If somebody gets 200 hours to do an ultra deep field in north, please come back to this field and observe the bottom of the main sequence in the LMC. That would be great. And that would also solve the angular momentum problem. But we didn't pick this field for extragalactic studies, even though the LMC is technically a galaxy, for this reason. So in the north, there is our deep survey field, an LBT image. The the purple circle is our 70-hour VLA map that reaches to below microjansky. JWST will cover pretty much this circular area, and HST has also covered it. And then there's all kinds of data, too much to speak of. It's an ordinary, clean, deep survey field. The only thing that folks like us might find wrong with it, it has somewhat too many brown dwarfs, like 9 times more than in good south, because you're at low galactic latitude. Now, there's a lot of astronomers here, even at ASU, who think brown dwarfs are really interesting, especially if you can see them all the way out to the edge of the galactic disk and monitor them as often as you want. You could actually be in the business of observing Jupiter-type great red spots going around to brown dwarf if you observe it often enough. So some folks are going to do that. But for an extragalactic survey field, I'll spare you the details from the hard X-rays to long wavelength radio. It has been observed at just about everything that's available, with the exception of, unfortunately, Herschel. We never got this field in front of Herschel because we didn't think of it while Herschel was alive. So we don't have the far infrared. But there is data there by a very large number of folks on just about every other wavelength. Again, it's not a deep field folks had looked at before, but it's there. and it looks ordinary from the ground, just a little bit of an excess of faint galactic dwarfs, which, as I said, is very interesting by itself. So because it's in the Hubble CVZ, it's been observed in cycle 25 and 28 in a cloverleaf fashion, which was the most effective way to pack the field in the rest or in the observed ultraviolet, as well as the B and the V filters. I should have said from the outset, James Webb doesn't take on until R band or 0.7 microns, and there the PSF isn't very good. So it's really 1 micron and beyond where it, to a great extent, will beat Hubble. So Hubble still needs to provide the optical, and it's doing that. With James Webb, we observe more in we call it a windmill fashion. And so here's the Hubble image. It has some holes in it that are currently being patched up. And the one thing that folks need to be used to with Hubble, you could, with HCS and with 3, make nice mosaics largely without holes. With James Webb, that ain't going to happen anymore. If you look at the focal plane, here's NIRCam, for instance, 2 modules, each work at short and long wavelengths at the same time with the dichroic, 8 detectors in short wavelengths, and then 2 larger pixel, same field detectors at long wavelengths. Something similar for NIRSpec with 4 detectors covering, or so 4 of these MSAs covering 2 detectors, defined guiding sensors, the nearest GRISM spectrograph, and the mid-infrared instrument. These kind of field of views, they don't overlap. So if you want to do the Hubble thing, having a parallel instrument trail the primary, let's say NIRCam is primary and NIRISS is parallel, you need to make sure that this field here with NIRISS covers what NIRCam has covered before. And the way you do that is with a windmill. You have with NIRISS, you make a strip, you get the GRISM spectra to about 28 magnitude in a couple of hours, between 1 and 5 microns. You have to choose your range, of course. And with NIRCam, you can make a chocolate bar this shape if you cleverly dither it. And if you repeat these 180 days later, the NIRCam part will overlap the NIRISS, and the NIRISS part will overlap the NIRCam part. So if you have a 4 epoch windmill, you can get the inner part covered with both spectra and images to about 29 and spectra to about 28 AB mag. That's about 5 sigma detection for point sources. If you do this more often, you get a more complete filling except for a central hole. There is better ways to do that by, actually not shown here, but you can also dense pack it and arrive at the same result. It's a little more expensive, but then you don't have holes. So there are ways in this part of the sky, without doubling the integration time, to get spectra and images on top of every point of the sky you're interested in, thanks to the parallels. So that's what we're going to do in our GTO time. And there's already a large number of folks, including the high redshift supernova hunters and the brown dwarf folks, that want to cover this with more epochs, either on short baselines or long time baselines. For instance, if you look, and this is not my field, but I talk behalf of Adam Rees and his group here, Steve Rodney, Lou Strolger, a whole bunch of other folks that are doing this, Saul Perlmutter, of course, to find supernovae, very high redshifts, either of type 1a or pair instability supernovae. If you imagine what these things might be like at redshift 7, of course, due to the time dilation, their light curves get stretched by a fair bit. For a type A, this red curve over here, for a type 2, this blue curve, and then for pair instability, 200 solar mass star going off supernova, this green curve, which stretches over 6 or 7 years. So you need to have time coverage on short time scales to lift out the 1As, and then on longer time scales to find the other supernovae. And this is what folks are going to do by following up on this field and some other fields, to be fair, to find some of these very high redshift supernovae. Okay, this would be a good time to start talking about the first light, the first stars. I want to see if there's any other questions on the time domain science so far. I'll look in the chat. I can't really do both.
I think there's nothing right now. So.
Okay, then we'll carry on. So we all know that WMAP and Planck in particular came down with very low optical depth for reionization, typically 0.05 and a bit. That puts the reionization redshift, if it were instantaneous, at 7 and a bit. Of course, it doesn't have to be instantaneous. And then there is this rather surprising result of the dip in the long wavelength radio background at 78 megahertz by Baumann et al. That potentially places some of the first star forming activity at redshift 17. I hear that this has been reobserved at roughly the same redshift, roughly the same depth, but a somewhat different shape. The end of this is not in sight yet. If this is real, we need to count on the possibility that the faint star, the first stars may be there at redshift 17. Let's imagine, though, that because of this significant increase in reionization optical depth between redshift 10 and redshift 6, that the main activity was in that redshift range of 7, 8. And let's then imagine what might have happened between redshift 17 and redshift 7, and I'll get to that in a minute. Let me first show you the Hubble Ultra Deep Field, as you're all familiar with it, all 592 hours or 841 orbits in 13 filters composed here. The limit is anywhere between 28 and 30 some magnitudes, depending on the wavelength you're looking at. You've all seen this image. Here's the same data. So it's very much the same data rendered for the infrared. So this is more what James Webb will see like, except it will add many more filters past 1.6 microns. The green circles are the dropout candidates at redshift 7, 7 and 8. The orange circles are a few dropouts at redshift 9. There's something inside each orange circle. And this one red circle is the only candidate we have at redshift 11. If you don't believe there's any, 11 means out of 13 filters, there were 12 non-detections and the H band had something in it. I will collapse all 13 filters into one, and you can see that there is something there in every circle. Now, whether that's truly a redshift 11 remains to be seen, but that's what we got. The important thing to quote here is that 45% of the Hubble sky pixels are covered with objects. So that's beginning to be a problem for, seeing background objects. You have foreground crowding. And for James Webb, of course, the pixels are smaller, but the depth is also per unit time going to be substantially more. So eventually we're going to run into the same problem with Webb, and that's maybe a good thing. That means it will be harder to measure blank sky. So let's look at the left here, the MADO diagram. Everybody familiar with that? Star formation history versus redshift. Peaks around redshift 2, slightly smaller, and then trails off all the way to redshift 8 and beyond. Here to the right, we see a prediction of what that MADO diagram would look like if you start with hydrodynamical simulations, in this case done by one of our students, and Evan Skanepiako with the Ramses code. Starts at redshift 18 at 0 metallicity, close to the Bowman redshift, but arbitrarily starting there. Star formation rate, of course, increases towards the lower redshift. The fraction of POP3 stars that's still there, of course, initially is very high, like 100%, as it should be, because they start with 0 metallicity, but that the fraction of classical POP3 quickly goes down to well below 10% by the time you reach redshift 8. And then, of course, it meets the data here. This blue line is the purple data here in the MADO diagram. Why do I bring this up? Well, because this allows you to do a number of things. One of the things you can do is integrate the sky brightness you could get for a star formation history. Let's say the MADO diagram extrapolates like something like this. You can calculate what the integrated sky brightness should be from these objects. And we published this in a paper in 2018. It's about 31st magnitudes per square arc second decay band as a reference. And that is similar to what there might be from objects that are not stellar, but contain a black hole component. And I'm referring here to the work by Cappelluti et al. And Kashlinsky et al., who have done a cross-correlation of the Spitzer data and the Chandler data. So imagine you have a Spitzer image like this. This is not Spitzer, it's Hubble. You remove all the objects, all 45% of the pixels with source extractor, and you look at the remaining sky where there ain't detectable objects. You do the same in Chandra, and you correlate Spitzer with itself. You get this signal here, which is the black points. And then you imagine what the foreground galaxies would have done, which is the orange line, or with James Webb, an orange line further down. And then you see this excess, this cross-correlation excess between 100 and 1,000 arc seconds, which is kind of your field of view with Spitzer, where it's non-zero. Well, some people have said it's all due to systematics like dark current plateaus and stuff they've left in. That's possible. At the very least, we can use it as an upper limit. The surprising part of this is that there's also such a signal. If you correlate the Spitzer data with the Chandra data at 2 keV, there's a non-zero signal that has now an amplitude in nanowatts per square meter per steradian squared to the the whole thing squared. And this only makes sense if this signal, and by the way, this signal is not seen if you take just the pure ACS data and correlate those with the Chandra data. This only makes sense if there is a glow out there of the order of 31st magnitudes per square arc second that is partially made by POP3 stars or faint galaxies, faint star clusters past redshift 7, and perhaps in part by stellar mass black hole accretion disks, which is what I believe is going on. It's a mix of the two. Let's assume for the moment that these data allow such an upper limit to exist. Then the question is, in the context of the extragalactic background light, which is now as a function of wavelength from the far UV to the far IR, if you integrate the galaxy counts, this is a paper by Driver et al. There's many folks have done this previously. The red dots, if you integrate that out and extrapolate, the counts converge, you get the red dots. The green curve here is the reflected sunlight, the zodiacal sunlight, plus the scattered dust by the zodiacal belt. The various models tell you how much light you can get from discrete stars and galaxies. And there is independent gamma ray constraints out there that give roughly the same answer, although there are folks that say there must be somewhat more diffuse light out there at various wavelengths. I'll leave that for what it is right now. If you take this 31st magnitude that I just quoted for both the extrapolated MADO diagram and for the black hole accretion disks, which I think are stellar mass black hole, you get these two orange and black upper limits here. Reasonable, but not proven. Let's assume that that's an upper limit and not a real signal. How many POP3 stars would that take? The answer is about 1,000 per square arc second anywhere in the sky. That's perhaps a somewhat high number. It's barely consistent with the metal production. Perhaps it's lower, 100 or 300. We don't know. I'll get to that in a minute. If it's a number like this, any of these surface brightnesses, whether they're diffuse or discrete objects beyond the current Hubble detection limit, could lead to caustic transits. And that's the last part of the talk. In this paper 2 years ago, we calculated that if you get this kind of infrared background from POP3 stars or the stellar mass black hole accretion disk, what's the chance that one of them will go across the caustic? I'll give you the quick answer. You get about 0.3 a year if you stare at one cluster a few times a year, if the surface brightness is indeed 31st magnitudes per square arc second. Surface brightness is less, you get fewer. But let it be roughly that number. If you observe 3 clusters, you might get lucky. And indeed, folks have gotten lucky with observing clusters with individual stars at redshift 1. You all know how this works. I don't need to dwell on it a lot, but if you have critical curves for a cluster here, redshift half, this case max 1149, in the source plane, an apology for my dog, I can't turn him off, you get, of course, with the scaling with the angular size distance to a redshift of 10, so now the area where this happens is smaller, you get this black widow spider web type structure, where towards the caustics, where in principle the magnification could be infinity for an infinitesimally small object, you have a d to the minus 1/2 behavior. So if there are objects very close to this caustic, you could magnify by this number here, a constant which is of the order of 10, divided by d to the 1/2. Now, this signal can be corrupted by microlenses from the ICL, so basically brown dwarfs and low mass stars that happen to be in the foreground cluster. But if this happens far away from the cluster center, you might get lucky and get a star at a redshift of 10 or beyond, go across the caustic and see it. It would have to be magnified by more than 10,000 to see it. This has been seen several times here by several folks, including folks in Princeton who worked on this, analyzing it independently. In this case, a B star crossing at a redshift of 1.5 across the Caustic was seen here at 2014 and here in 2016. And I think it's a fairly convincing case that in this cluster, which was also 1149, an object with a spectrum of a B star redshift 1.5 underwent some magnification event that was clearly more than you ordinarily get with a small galaxy that's a half an arc second across lying on a Caustic. So if the Caustic is clean, you can get this extreme magnification because a redshift, not so much 1.5, but redshift 7 to 17, these POP3 stars, which are anywhere between a few and 100 solar radii, are of the order of 10 to the minus 11 arc seconds across. So 1 over the square root of that is a large number. You could, in principle, get a factor of 100,000. In practice, you may not get quite that much, and this was also done, work done by folks in Princeton here, as well as by Diego et al. You could get magnifications that are bigger than 10,000. And as objects go across the Caustic and subsequent microcaustics, they can be magnified several times. So it would be useful to observe these clusters a couple of times a year for 10 years or even 15 years in a row, if you can help it. And then as Miralda Escudé pointed out, if you go from a single caustic to something that has micro lenses in the foreground from the cluster ICL stars, you corrupt this caustic and you make it like a corrugated surface where lensing happens multiple times, as you can see here. So if you go through this calculation, here's another example by Kaurov et al. And Chen et al. More recently, and I think Brenda Fry was also involved in this, a B star at redshift 0.9 with a magnification of several hundred. There's other folks here that can say this much better than I can. Here's another cluster, a Planck selected cluster G165 that has lensed arcs at redshift 2.2 and lensed families, and it's clusters like this. We plan to observe 6 or 7 of them in my GTO time, in the hope that we might find some of these POP3 stars. And here's our MESA code POP3 HR diagram with masses between 1 and 1,000 solar masses. Of course, they live very quickly on the main sequence and the giant branch of the order of a few million years, up to several hundreds of millions of years for low mass stars. It is these stars over here, especially the heavy ones that produce black holes, and the mid-range between 30 and 100 or so solar masses that produce black holes, exactly in the range A, where LIGO has already seen them, 30 to 50 solar masses, and B, as long as the metallicity is not exactly 0, which it would be for the first generation, but maybe the second generation wouldn't be, these things are believed to more often than not come in binaries. So if you get a high mass star with a lower mass star, you can have a 3 to 5 solar mass star live on the AGB, while this massive star already has formed a black hole, and you can have the asymptotic giant branch of the mid-range stars feed the stellar mass black hole that we see with LIGO today. And so the conjecture is that more often than not, these massive stars will come in binaries, perhaps equal mass, perhaps unequal mass. And the upshot is that if you do the stellar mass black hole accretion disk calculations for these, you get more or less exactly the same surface brightness and more exactly the same radii as you get for these massive stars, with the only exception that these multicolor accretion disks around the black holes, of course, are much hotter in the center. They reach X-ray temperatures, while the POP3 stars never get hotter than 105,000 degrees. So if you want to have a Spitzer-Chandra X-ray correlation in the sky, you need to use these kinds of black holes, whether they're primordial or not. I think they may be leftovers from POP3 stars. If you feed this all through the calculations, you will find, I'll spare you the mass luminosity relationship and the actual calculations, you will find that to the detection limit of JWST 29th magnitude, you could get for surface brightness of 31st magnitude per square arc second in the sky of these objects on average, whether or not the mini galaxies on the Caustic or whether you just hit an arbitrary background POP3 stars, that if you observe a cluster about a few times a year, 3 clusters in a row, you might get lucky and find one of them. And I think more often than not, you will find a stellar mass black hole accretion disk that goes across the Caustic rather than a POP3 star, but you could get a combination of both. So I'll leave you with these conclusions. The time domain field will produce very exciting science on high Z supernovae, weak AGN, brown dwarfs, and anything else that varies or moves. We think we might even find some Oort cloud objects that are visible, but that's another talk. And then this is it for the stars and the stellar mass black hole accretion disk. So for the sake of time, I'll stop. I'll be happy to have more questions, and I have more spare charts to answer questions, of course. Thank you, folks.
Thank you, Roger, for a beautiful talk. Do we have any questions?
You look at the chat.
Asking question to Roman. Could I ask?
Yeah, go ahead, please.
Hi, Roger. Beautiful talk with the dog house and dog. So for detecting the POP3 stars, what's the rest frame wavelengths are we looking at?
We're all looking at, so let's see. I'm going to get to my spare charts here. I meant to say, do not forget the proposal deadline and don't miss the boat because it will be a feeding frenzy, okay? It will be like Hubble in the first couple of cycles. So I have a chart on this somewhere. Let me see if I can find it. So these are the filter sets we use for NerdCam, and of course MIRI provide longer wavelength filters. So anything past redshift 7 will not be seen in the 090 filter or the 115 filter, but seen in the other filters. And this, of course, is for a mini galaxy. But when a POP3 star at Z of 10 goes across the Caustic, it will produce a very similar SED, just a single stellar object. But it needs to get lucky on the Caustic and be magnified by 10,000 times or more, because intrinsically it will be between 37th and 42nd magnitude.
And you're assuming there's no dust obscuration, anything to attenuate it?
We assume that the POP3 stars themselves initially aren't in a very dusty environment. That could be wrong. If they're never visible, then you can't see them. You'd have to go to longer wavelengths. But we're looking at rest frame UV here. So this is the Lyman break, of course, if you can see that. And we will look all the way up to 4.5 microns where we're in the mid UV.
Thank you.
Yeah.
I think Paul has a question.
Please.
I was struck by just how much effort has gone into building this wonderful instrument for over 20 years. And the lifetime is expected to be less than something, 20 years. I think I saw 14 on one of your slides.
Yeah.
So what that means is whatever comes after JWST, if we want something that will take its place, we really need to be working on that right now.
Yes, we do.
So what is that?
Well, as I alluded to before, JWST is the smallest one they ever made of this kind. So if you like to get a 12 meter or a 15 meter, you could. You just have to convince the decadal survey. And of course, JWST has to launch first and it has to be successful. We had hoped 10 years ago that this would have happened by 2018, that we could show the decadal, look, this works. Now build a 16 meter. It's too early for that, I think. I don't know what the decadal is going to say, but we want to make sure that this works. And then if we can make the case that we want to have a UV optical telescope that's twice as large, one could make that. Of course, it will not be cheap. These things are always harder and more expensive than you think. Go ahead. Somebody else asked the question. I hope that's a good answer. So yes, the younger generation will need to think about building maybe a UV optical sequel to James Webb based on the same technology.
Yeah, next question, Neda.
Yeah, hi, Roger. Wonderful talk. Good luck with everything.
Thank you.
I have a question on this excess correlation from Spitzer to with Chandra.
Yeah.
and you're putting it in terms of the first stars. Now, how much of that could be just the extension of faint galaxies, faint AGNs, which does make most of the X-ray extension background?
It could be, but faint AGN, unless they're dust obscured, and of course the X-ray doesn't necessarily care much about that at the right wavelengths. The AGN would show up in the images, and the way this cross correlation is done, you take the images, you remove every discrete object, and then you do the cross correlation. So it would have to be very faint QSOs.
But do you remove any extension to a possible luminosity function of these faint galaxies beyond the threshold of what Spitzer can see?
No, you don't. And that's something you could theoretically do. I had a chart on that if I can show it. Wasn't going to show it in the talk, but if you study the last 10 years worth of Hubble with how the Schechter luminosity function evolved, you know, good Lord has given us 3 Schechter parameters: the faint end slope, which gets steeper with redshift, the pi star, which goes down in amplitude rather uncertainly, but it does, and the M star, which behaves like the MADO diagram that shows where most of the action is. The intermediate redshift at -21, and then perhaps it goes down, but not by a lot. If you take that Schechter landscape at face value, basically extrapolate along these brown lines, you get this rainbow diagram, and that partially answers your question. Get my talk thing out of the way here. So to the various limits, this is the area you observe, and this is the shallow limit we observe, and then you can go deeper surveys over here to about 30th magnitude, or you could do lensing surveys. And then your question is, how far do you extrapolate this luminosity function, both in the optical or X-rays, infrared or X-rays?
Right.
The answer is in the next questions. If you take the previous relationship at face value and you just extrapolate around this 0.7 line, you get this diagram, and that's a possible behavior of the Schechter function. I think it keeps going, but then past about -13, I think it will start dissolving into individual stars and star clusters, because this is the range we expect the POP3 stars themselves. So I think you're no longer looking at outskirts of galaxies or cooling flows around galaxies or black holes. I think you start looking at individual objects, but that's my guess.
Right. But will that change your predictions of how many of these first population stars you can see?
No, it doesn't. It actually happens to give exactly the right answer. And I'm sorry, I have to track back to one more chart that I skipped. So this black line is the theoretical prediction of the mass luminosity relationship for zero metallicity from the MESA code. There is no star formation theory in that, just stellar evolution. And if you weigh that with any reasonable IMF, you know, salpeter like this orange line, or top heavy like this blue line, or an alpha slope of 2, you get one of these 3 curves, which shows you where most of the light luminosity density comes out. And the answer is between 20 and 200 or 300 solar masses is where most of the light is produced for any reasonable IMF, because the mass luminosity relationship, you know, unlike the slope of 3.5 we learn here in the textbooks, is actually quite flat at the high mass, and it's a slope of almost 1. The corollary of that is that when you go below the detection limit of HST or even JWST, I think you start looking at individual stars eventually, and they will be between 20 and 200 solar masses.
Yeah.
And if you integrate out this luminosity function, I did this for fun, I have to write it up, you arrive at a sky brightness that's exactly 31st magnitude per square arc second. So I think this picture could be right. I haven't proven it, but I think it could be right and give you roughly the observed infrared sky brightness that the Spitzer folks claim is there. But because the Chandra folks also claim it's there, I think a logical explanation that it must be in part black holes, and my preference would be for many black holes. Yep. How's that?
Sounds great.
Yep.
Thanks. We do have 2 more questions, but we are out of time, I think. The call lunch happens in a short 23 minutes. So maybe you can ask Roger the questions at lunch instead. And for now, we can thank Roger again and just see each other again in 23 minutes.
I'd be happy to answer more questions. I see one here from David Weinberg. Thank you again all for letting me give this talk. David, I'm reading your question, Nancy Grace Roman.
That wasn't a question, it was just a response to Paul Price.
Ah, okay. Yeah, so if you look at this rainbow chart, there's a lot of good stuff to be done there for the white fields, right? If you could get this orange line down to hundreds of square degrees, especially if you have infrared capability, and there's currently an interesting discussion going on to add a K-band filter to Roman Space Telescope, even though it doesn't have cooling, but a short K might be useful. You could begin to pick up, if this Schecter landscape is right, not only some of the faint quasars that this little rainbow here sort of indicates, probably not very correctly, but you might also see some of the bright end Schecter, and some people have argued it's actually not a Schecter function, may continue as a power law at the very high redshifts, at redshift 9 or beyond. And so that would certainly be worth pursuing with the Roman telescope. And somebody asked about CAC from the ground. What can CAC and the next generation do? Of course, JWST will do this caustic transit business only for 10 or 14 years at most. And we saw that, you know, some of the work also done in Princeton, that these light curves going across the caustics and microcaustics may stretch for 20 or 30 years. Eventually, you need, you know, 29th magnitude H and K band follow-up on timescales of decades, and the 30 meters on the ground could do that, I think. With some effort, but they could. All right, I think
that's all of the questions.
Thank you all for coming. Very good questions. And so, then we'll have the lunch in 20 minutes.
You can log out. The call lunch is a different link, so just check your email. You don't come back here.
Yeah. And that's in 20 minutes, right? Just for the record.
20 minutes. Yes, exactly.
Yeah. Okay. We'll see you there.
Great.
Thank you all.
See you there.
Great question.